Welcome back, and we continue our discussion on biometry. This time we start with axial length. So when we talk of axial length measurement, we are talking about measuring the distance from the corneal epithelium to the retina. However, this distance from the corneal epithelium to the retina may differ between an ultrasound scan machine and an optical biometry. The optical biometer measures from the corneal epithelium to the Bruch membrane or the retinal pigment epithelium. The ultrasound scan machines measure the distance from corneal epithelium to the inner limiting membrane of the retina. Like we talked about in part 1 while discussing keratometry, the importance of right keratometry measurement. The same way we discuss over here the importance of axial length measurement, the right calculation of axial length, measurement of axial length. So in this formula, the SRK formula, you can see power is equal to again A constant minus 2.5 into axial length minus 0.9 K. What this means is that if we make an error of 0.3 millimeters in axial length calculation, that can lead to 1 diopter of error in final IOL power calculation. Or in other words, for every 1 millimeter of error in axial length calculation, this can lead to 2.5 diopters of error in IOL power calculation. Well, this is for average eyes. For short axial lens, this error can be magnified. Well, in the last slide, we discussed that 0.3 millimeter of error in axial length calculation can lead to almost 1 diopter of a difference in IOL power calculation. Let's work out that in SRK formula. Well, we know that SRK formula is no more used today. It's a very old formula. The current version is SRKT. But SRK formula, this formula kinds of gives us a sneak peek into what could be the impact in final IOL power calculation, right? So here we take the correct axial length as 23.3 and we wrongly measured it as 23, the E constant and the corneal power being the same in the example. So the correct axial length is 23.3, but we measured it wrongly 23 millimeters as the axial length. The difference in IOL power is 0.75 diopters as per the SRK formula. In the next slide, we will see what is the difference in final IOL power if we make an error of 0.3 millimeters with the currently used SRKT formula. So here is the SRKT formula which many doctors use, and SRKT is the updated version of the SRK formula. So with the 43.5 as average IOL, average keratometry reading, axial length of 22, anterior chamber depth of 3.0, and A constant of 119, the IOL power calculated is 26.3. With the same keratometry readings, anterior chamber depth and A constant, here we have an axial length which is 0.3 millimeters less. Say for example, we calculated the correct axial length was 22, but we wrongly calculated as 21.7. The correct axial length was 22. So there's a difference of 0.3 millimeters in axial length. The IOL power comes over here as 27.35. So the difference is more than 1 diopters. So you can see over here with the current generation formulas, the SRKT formula, for example, it shows us that if we make an error of 0.3 millimeters, the difference, the final impact on IOL power we will be off by more than 1 diopters. Such is the importance of axial length measurement a correct axial length measurement. So in the mid-70s, with the advent of the biometry machines, we could measure the axial length. That was basically the time of mostly anterior chamber IOLs. Axial length was measured by A-scan machines, the contact A-scan machines, that is ultrasound contact or applanation based ultrasound machines, and also later on immersion based biometry machines came on, which was also an ultrasound machine, but you measured it with immersion technique, right? That is, the probe was coming in not in contact with the cornea, but the probe was dipped in a fluid filled path. The average axial length of a patient is around 23.5 millimeters, around 23 millimeters to 24 millimeters roughly. That's basically the average axial length. And in the last few slides back, we talked about that with the ultrasound machine, the measurement of the axial length is the measurement of the distance from the corneal epithelium to the inner limiting membrane. So let's discuss the science of the ultrasound machines. The A scan stands for amplitude scan. A probe with a transducer sends a wavefront or ultrasound waves for 80 nanoseconds and listens to about more than that time, around 200 milliseconds. When the ultrasound returns, it makes the transducer move back and forth, which then is turned into electric signals. This electrical signal is passed through an amplifier so that its signals improve in strength. Therefore, the name amplitude scan, A scan. These signals are then transferred through a rectifier to convert the negative sine waves into positive sine waves, and in all in one direction, so that they could be interpreted in this graph over here. So you can see these waves, the sine waves over here, and this basically helps us to understand how well that measurement has been taken. So the echoes received back into the probe from the interfaces are converted by the biometer to spikes arising from the baseline. The greater the difference between two media at each interface, the stronger the echo and the higher the spike height over here. The spike height is affected by the difference in density and by the incidence of the probe beam. If the probe is held not parallel, then part of that echo is reflected away and you will not get a spike which actually arises from the baseline at an angle of 90 degrees and of equal height. A perfectly high, steeply rising retinal spike may not be achievable when macular pathology is present. That is, if the eye has an epiretinal membrane or a macular pathology like macular edema. So let us now try to identify these spikes over here. We now understand their reflections from the ocular media. So the first spike over here is the spike of the cornea, the anterior and the posterior cornea. And since you are seeing the corneal spike, both the anterior and the posterior, the measurement must have been taken by an immersion ultrasound. Then comes the anterior corneal spike and the posterior corneal spike here. Then comes the retinal spike, and immediately after the retinal spike, you will find this scleral spike, and after the scleral spike it will be followed by orbital fats. All these spikes should be of equal height and they should rise 90 degrees from the baseline. That guarantees you a good measurement. Now, what we mean by axial length, as I said before, is the distance from the corneal epithelium to the retina. Now, it is important to understand that the biometry machines do not measure the distance, but they basically measure the time that the ultrasound takes to reach the retina and come back. If we know the speed or the velocity of the sound in each of this medium, then we can use the formula speed equal to distance by time to get the distance, that is the axial length. So distance is equal to velocity into time, that is the velocity of sound through each of these mediums into time that it is taking, the ultrasound is taking to come back to the probe. If we know the velocity and the time, then we can easily calculate the distance, that is the axial length. Another aspect that needs to be discussed over here is that the phakic axial length is, the phakic velocity of sound is 1550. Phakic means when the lens is there. So when the human crystalline lens is there in the eye, then the group sound velocity, that is the average sound velocity in the eye, is 1550 meter per second. When you remove the crystalline lens, that is the eye has no lens in it, in the aphakic state, the sound velocity, the average sound velocity is 1532 meter per second. The pseudophakic sound velocity is 1532 meter per second plus the correction factor of the lens. When do you need to measure the axial length in the pseudophakic state? You may want to measure the axial length in the pseudophakic state to compare with the phakic axial length. For example, if your surgeon has run into a refractive error after surgery, he may want to see whether the axial length was calculated in the phakic state. To do that, he has to measure the axial length again in the pseudophakic state, because now he has implanted the intraocular lens and he's measuring the axial length post-operatively. So he has to use 1532 meter per second as the sound velocity and add a correction factor of the lens. For example, if he's using an acrylic lens, he can use a correction factor of 0.2. So whatever the pseudophakic axial length he finds out with this sound velocity of 1532 meter per second, he has to add 0.2 to that axial length that he has found out. For example, with pseudophakic axial length, if the pseudophakic axial length with 1532 meter per second is 23, and if he has implanted an acrylic IOL, then he has to add 0.2 to that 23. So the axial length would be 23.2. That axial length has to be matched to the phakic axial length to rule out that the refractive surprise has not been because of a mismeasurement of a wrong measurement of axial length in the phakic state. So the question I think we have already covered in the last slide: why do we measure pseudophakic axial length? Well, to reiterate that, we measure the pseudophakic axial length to compare to the fellow phakic eye for accuracy. For example, if the patient is having already an IOL in one eye and he has come for the second eye, you want to match the axial length of the two eyes, because the two-eye axial length difference should not be more than 0.3 millimeters. If the patient has already an IOL in one eye, to compare it with the phakic eye, you have to measure the pseudophakic axial length, and then add a correction factor. The correction factor for the acrylic IOLs is 0.4. Sorry, it was not 0.2 in the last slide that I said. It was 0.4. The correction factor with EMMA lenses is 0.2. So you get the pseudophakic axial length and add 0.2 to that pseudophakic axial length to get the final axial length to be comparable to the phakic axial length. You also, as I said before, you measure the axial length, pseudophakic axial length, to understand if there has been a refractive surprise. If you want to do an IOL exchange, you want to have to measure the pseudophakic axial length. So use correction factors with measured pseudophakic velocity of 1532 meter per second. A scan of pseudophakic eye may be associated with multiple reverberation echoes in vitreous cavities. So if you have measured the pseudophakic axial length, you will see that there may have been a lot of echoes because of the echoes coming from the vitreous cavity. And there you might need to decrease the gain basically for the machine. The gain of the machine may have to be decreased in order to get rid of this multiple echoes, which can lead to inaccurate reading of the pseudophakic axial length. So we know that ultrasound A scan could be of two types. It could be contact or applanation, or it could be immersion. In applanation or contact-based biometry, ultrasound biometry, the probe comes in contact with the cornea. So typically to anesthetize the eye, we use topical drops. And remember, in part 1 we discussed that wherever you are doing an applanation contact biometry, you should always do the keratometry first and then do the applanation, because you do not want to put a drop and then do the keratometry reading. So always do the keratometry reading first. While patient is seated, ask him or her to fix it on the red light of the probe. If the patient fixates on the red light of the probe, then only the rays or the sound rays are going to go and hit the macula and come back to the probe. If the patient is not fixating, then the rays will not come back. That is, the sound reflections are not going to come back to the probe, and you are not going to have a good reading. One challenge with the scan machines with contact biometry, contact or applanation ultrasound is the corneal compression. Because here the probe is touching the cornea, there's every chance that you will indent the cornea, you will press on the cornea. If you press on the cornea more, then what you are getting is a lower axial length. Say for example, the patient's true axial length is 23 millimeters, but you may get a lower axial length from that. Can you tell if you get an axial length which is lower than what it actually is, what kind of error the patient is going to suffer from? Post-operative refractive surprise. What kind of post-operative refractive surprise it is going to be? Well, it is going to be a myopic surprise. Why? Because here the patient's axial length, true axial length is 20, say for example 25 millimeters. But because of corneal compression, you get an axial length of say 24.7 millimeters. That is 0.3 millimeters less than the true axial length. So then your IOL power, because you have measured a shorter axial length, your IOL power will be more. You will go for a higher IOL power. But the patient's axial length is not 24.7, but it is 25. But if you go for a higher IOL power, you will get a myopic surprise. The rays of light will converge before the retina. And it is because of this reason that surgeons worldwide have moved from contact ultrasound biometry to immersion ultrasound biometry. Another challenge with ultrasound biometry is the misalignment of the sound beam, and especially when the patient has very hard cataracts, it is very difficult for the patient to fixate on the red light. In those cases, you may have a misaligned sound beam, and the sound sound beam is not going to hit the macula but somewhere else, which may lead to a wrong reading. At this stage, it is important to understand that for every 1 millimeter of error in corneal compression, for every 1 millimeter of corneal compression, that is, you are making a 1 millimeter of error in axial length measurement, in the normal eye, this could lead to an error of 2.5 diopter in IOL power calculation. For a short eye, this can lead to over 3 diopters, 3.5 to 3.75 diopters. For the long eye, that could be an error of 1.5 to 1.75 diopters in IOL power calculation. We mentioned about immersion biometry. What is immersion biometry? In immersion biometry, your probe does not touch the cornea. Therefore, there is almost no chance of indenting the cornea, compressing the cornea. The probe comes in contact with a fluid-filled bath. So this is often called a shell. In some companies call it a Prager shell. And that Prager shell is filled with BSS or fluid. And the probe comes in contact with that fluid. When you measure the axial length with immersion biometry, there's every chance that you will see both the sides of the cornea, the anterior as well as the posterior cornea. But when you measure it with applanation A scan, that is, you measure with contact ultrasound, you will see only one corneal spike. The advantage of immersion biometry is that it eliminates corneal compression. However, in some cases, it may result in a longer axial length measurement. And we also need to be, mindful that there could be sometimes air bubbles inside the Prager shell, which might affect the measurement. So in certain special cases, ultrasound biometry may not be the right option. For example, posterior staphyloma. What is posterior staphyloma? Posterior staphyloma is a condition where the patient's anatomic axial length does not match with the refractive axial length. That is, its fovea is not located where it is supposed to be. In these cases, when you do an applanation A scan or an immersion A scan, you do not know that the patient has a posterior staphyloma, and the probe beam actually reaches the furthest point in the posterior pole where the fovea is not located. Therefore, you may tend to get higher axial length, longer axial length than what it actually is. In these cases, you may end up with an hyperopic surprise. Why hyperopic surprise? Because the axial length was supposed to be 25 millimeters, but we wrongly measured it as 25.3 millimeters, for example. In that case, what are we going to do with the IOL power? We are going to choose a lower IOL power. But the patient's axial length is not 25.3 in reality. The patient's axial length is much shorter than that, 25 millimeters. Therefore, the patient may land up with an hyperopic surprise. One option for such patients could be the B-scan. B-scan provides cross-sectional display of diseased tissues and is valuable in detecting unsuspected posterior segment diseases. The frequency used in diagnostic Ophthalmic ultrasound for posterior segment is around 8 to 10 megahertz. This B scan is an option for patients with possible posterior staphyloma. In posterior staphyloma, as I said before, the anatomic axial length is higher than the refractive axial length, which could lead to an hyperopic surprise. This, again, B scan could be done for premium lenses where the stakes are very high and the patient has paid from out of the pocket. When does the surgeon understand that he might need to do a B scan? Well, he has to be suspicious of posterior staphyloma for very high myopia patients. If he finds axial lengths longer than 26 millimeters, because such patients may have posterior staphyloma. If he gets inconsistent axial length readings, that is the standard deviation of axial length of all the 10 readings in the A scan is very high. A very high standard deviation may indicate posterior staphyloma, or if he gets an indistinct retinal spike. We discussed about the challenges with applanation biometry or with immersion biometry. The challenge for applanation biometry is corneal compression, which might lead to myopic surprise. The challenge with immersion biometry is that sometimes you might get a longer axial length, which may lead to an hyperopic surprise. The answer could be optical biometry. The first optical biometry was the IOLMaster, which was introduced around 1999 to 2000 and was based on partial coherence interferometry. The first optical biometry machine was introduced around 1999-2000 and was the IOLMaster, which was based on partial coherence interferometry. Simply put, it is the laser light that goes inside the eye, bounces off the retina, and is captured back by the machine. The optical biometry axial length is a measurement of the distance from the corneal epithelium to the Bruch membrane. Remember, in A-scan machines, ultrasound-based machines, we measure the axial length as a distance from the corneal epithelium to the inner limiting membrane. Optical biometry machines, since they apply laser lights of over 700 nanometers, they can penetrate and then go up to the Bruch membrane or the retinal pigment epithelium. So this picture actually explains us about the difference in optical biometry and ultrasound biometry. Ultrasound uses a sound wave of 10 megahertz, which is quite broad and that cannot actually penetrate the retina. It goes up to the inner limiting membrane of the retina. While the IOLMaster or other optical biometry machines uses a laser beam of wavelength of light more than 700 nanometers, 780 nanometers for the IOLMaster 700, IOLMaster 500, and it goes up to the retinal pigment epithelium or the Bruch membrane and reflects back. This is a major difference between the ultrasound machines and the IOLMaster. Several studies have been conducted to understand the accuracy of axial length measured by contact or applanation-based biometry machines, immersion-based biometry ultrasound machines, and the optical biometry machines. And here is a comparison between the three. Here is a biometry data. Can you tell me what is the challenge with this kind of biometry data? Well, you are correct. We only have got one eye biometry done. In the absence of the other eye details, it is very difficult for us to compare between the two eyes. As we understand, that the comparison between the two eye is very important to rule out wrong measurements. For example, in keratometry readings, we found out that a difference of 1 diopter between two eye corneal readings calls for another round of measurements of the cornea. Similarly, in axial length measurements, it is very important to see that the two-eye difference in axial length should not be more than 0.3 millimeters. Remember, an error of 0.3 millimeters in axial length for a normal eye can lead to 1 diopter of error in IOL power measurement. Therefore, two-eye differences of more than 0.3 millimeters is a problem and therefore needs to be checked again. Like in part 1, we discussed about the keratometry pearls. Here we discussed about the pearls for axial length measurement. Remember, like keratometry, what is important in axial length is measuring both eyes and comparing between the two. The difference in axial length measurements should be less than 0.3 millimeters. If it is not, we should repeat the measurement. We should also, wherever possible and available, we should correlate the axial length with subjective refraction. Does the refraction correlate with the total length of the eye? For example, you see a hyperopic patient. In a class, he's wearing +2. But in the axial length, you find quite high axial length, say 25 millimeters. This does not correlate very well. So it is very important for us to see why the axial length is not correlating with the subjective refraction. Remember, the average axial length is between 23 to 24 millimeters. So an axial length which is higher than 24 millimeters would be branded as a myopic axial length. Or myopic eye will have a higher axial length normally. For an axial length which is less than 23.5 millimeters, 23 millimeters, less than 23 millimeters, it is an hyperopic eye. This needs to be correlated. A B scan should always be done where the axial length is more than 26 millimeters to rule out, remember, posterior staphyloma. There's something called signal to noise ratio in the IOLMaster 500 and also in some other machines like the Tommy OS 2000. The signal to noise ratio should be high. Then only we can guarantee that the axial length measured is correct. Because if the noise is too high, then the axial length measured may not be accurate. The foveal pit visibility in IOLMaster 700. IOLMaster 700 has a foveal pit visibility, which should be seen. If the foveal pit is not visible over here, then it may mean that the rays of light was not actually directed to the fovea, but somewhere else, and the patient was not fixating. So this is the foveal pit, which is available in the IOLMaster 700. In the lens star, you can also correlate with the spikes, like what we do in an ultrasound A scan. So in the lens star, you will also find the spikes here, and you can correlate it.